to join you all this afternoon or this morning or this evening or whatever it is for wherever you are. So I'm joining today from the unceded lands of the Jabugai people, and I pay my respects to the traditional owners of the land on which I live, breathe, work and play. So the Indigenous people of the land and sea country here in Australia. And for many of you that may not have heard of the region, this is in Cairns, which is far north Queensland, Australia. And I wanted to talk today about the many different fashion changes that I've seen in mapping coral reef environments over my career. So I started working in this area in the late 90s, and I've seen a lot of changes. So I kind of want to share a little bit about that. And I'm also really, really happy to take questions as we go along. So if you do have anything at all, please pop it in the chat or comments as we go. That's perfectly fine. It doesn't distract me at all. I'm used to it. So anything that you want to pop in the chat, that's great. And I'll probably be asking you questions. So probably a good idea is to have the chat open and you can respond to me as well. All right, so first of all, I wanted to take you back 20 years. So have a think contextually about what 20 years ago looked like. So we were watching The Castaway at the movies. So good old Wilson and Tom Hanks there. We were listening to Britney Spears do it again in her wonderful lycra outfits. And I'm not sure how global the next image is, but certainly a huge one for Australia and really common at this time of year in particular is the 20th anniversary of Kathy Freeman winning the 400 metres sprint at the Sydney Olympics in an outfit which, strangely enough, kind of looks a little bit like Britney Spears there as well. So that's what was going on 20 years ago. And so now I want to take that to thinking about what remote sensing, coral reef remote sensing in particular, has looked like over those past 20 years, now that you have a bit of a feel for what 20 years in our life actually is like. So I'm a geospatial scientist and I'm interested in location. So largely this means if you've ever used say a fitness tracking device to measure how far or how fast you've run, how about you pop in the chat, just let me know with a Y or an N for yes or no if you have a fitness tracking device that would use GNSS or global navigation satellite systems to track how far or how fast you run. Right, yeah, excellent. So quite a few people have those, as do I. What about if you've ever used some device or mapping application to let you know the fastest way to get from point A to point B? Give me a Y or an N. Yep, I'd be pretty surprised if there are many people that haven't used some kind of device like this, right? And so again, this is using global navigation satellite systems, or really more commonly known around the place as GPS, but not really correctly known as that. What about if you've ever jumped on Google Earth to maybe check out where you live, your house, or maybe even a holiday destination or where you can go when you get out of lockdown or something like this? Yeah, great. So most people, and I'm pretty sure most people would be pretty familiar with this pop-up that comes on pretty much every time you want to download an app, right? Asking you if you can enable location services. So basically what underpins all of these things is geospatial information. And for me as a geospatial scientist, what I guess is a little bit different about what I do is that I don't just consume geospatial information, which everybody does on a daily basis. I create it and I analyze it as well. So that's the framework under which I'm going to talk to you about some of the work that I do. And so I actually got involved in remote sensing in the late 90s as a student, as an undergraduate student, and I work a lot with satellite images like what you might see on Google Earth. And the main reason I got involved in this is because not only do I like looking at the images themselves, but I realized that the best way to make maps of an environment is actually to get out in the environment itself and to experience it. And I realized that I could actually get paid to go scuba diving on the Great Barrier Reef or snorkeling or even camping in some of Australia's really beautiful national parks. And I thought, yeah, that sounds like a pretty cool career to be able to get into where someone pays me to go and do the things that I would otherwise pay to. So that's how I got started in this whole area. And so what I'd like to do is to actually take you to the Great Barrier Reef and share with you some of the things that have changed over the course of my career. So here we have the North Queensland coast here, and you'll see the Great Barrier Reef at this full extent. So it's actually made up of about 3,000 individual reefs. It's not just one reef. And so the whole area, if we put it all together, is about the same size as Italy. It's a pretty large region. But today I'm largely going to take you to the southeast region here. This is the Southern Great Barrier Reef, or the Capricorn Bunker Group. And in particular, I'm going to take you to this little reef. So just one of 3,000 is what I'm largely going to talk to you about, but it actually applies to many reefs around Australia and also globally as well. So welcome to Heron Reef. This is the reef where I've spent a large portion of my research career working, because primarily it's a beautiful place to be. And so if you think about this, I like to think about it as an upside down dead rat. So we have the eye of the rat, which is an island. And that island has some national park. It's got a research station for the University of Queensland and a resort there as well. So it's an absolutely spectacular place to go to if you get the opportunity to be as a researcher, but even as a tourist as well. So that island is 800 metres long. So it's twice around a football field. Twice around a football field, and 400 metres in the north-south direction. So just once around. So it's pretty small in compared to the reef itself, which is 11 k's in the east-west direction and 4 kilometres in the north-south direction. And just remember again that this is only one of 3,000 reefs. So, you know, when you think it kind of looks kind of big on that screen, it's just really a teeny tiny spot in the Great Barrier Reef as a whole. So ultimately what we're trying to do when we're thinking of coral reef remote sensing is to look at the different habitats on the reef. At least this is my main aspect of it. Look at these different habitats and see if we can categorize or map those in some form of remote sensing data, so satellite images or aerial photography. And largely my biggest question, it's a really, really simple question, is quite simply, how much live coral do we have on the Great Barrier Reef? So it really is as simple as that, because fundamentally we don't know the answer to that question. Again, 3,000 reefs, size of Italy, it's a pretty big question to answer. So we have some estimates, but nobody actually knows for sure. So if we're thinking about climate change and into the future and understanding if things are declining or if they're growing, we can never know the answer to that unless we know the baseline in the first place. So that's really what drives my research. So looking at these different habitats, being able to map those in remotely sensed data. And so now if I think about how things have changed over the course of 20 years, for me, the first one as part of my career is fieldwork. So this is a photo of me back probably in the late 90s. And I used to dive a lot as part of the work that I did. I never dive as part of my research anymore. So this is a sad aspect of how things have changed. Partly that's because of the insane level of paperwork that needs to be done to continue to dive, but also it's because of the other tools that I need to use, and I can't be in the water and be on land flying drones and other things at the same time. But it is a little bit sad when I think about the amount of time that I used to be able to spend in the water. That's really just not possible with the current structures that sit around working in a large research institution. Just make life a little bit too hard. That's probably my only downside of what we see through here. But largely what I'm trying to do is to come up with maps like this with satellite data. And often we do field work to be able to give us ground or in-water validation as to what we actually see there. So here's a map that would say, yeah, we have coral, we have algae, etc. And we need to be in the water and getting field data validation so that we know how accurate these types of maps are. Now, sometimes we don't use these hard categorical boundaries and we're looking more at quantitative mapping variables. And again, so this is some of my work from the early 2000s, still really asking that same question, can we map live coral cover? And so that instead of it being that categorical classification of coral, algae, sand, it's really about, well, what's the percentage of coral? And that's something that I still haven't nailed over the past 20 years. But fieldwork supports us getting these types of information. And so it's just the fieldwork aspect that I want to discuss a little bit more here in terms of how that's changed. So So we look at the different types of fieldwork that we might undertake. We might have a boat that has a video camera or a standard camera off the side. Sometimes we'll have people under the water and going along transects, taking photos, if you like. So something like what I'm doing under the water there. And we've also in the past worked on this sort of thing where we measure out a really large grid. This is what it looks like underwater, and then really surveying that in detail underwater. And first from some really early work, getting some video footage and then stitching those things together to get constant information over a region about the types of habitats that we see. So some of the work that we do now that has evolved, I guess, from over the past 20 years is the camera equipment that we use. It's obviously far superior to what it was 20 years ago. And digital, of course, as well. So obviously we can take many, many more photos. And you'll also see that that one of my colleagues here, while she's swimming along, you see this lead going up to the surface. There's actually a buoy at the surface here, and it's got a GPS on the top, which is giving us information about location. So I'll come back to that and how that's changed over the past few years as well, and why that's critical for our field survey work. We have some tech that's really not tech. So we use child toys, and in this case, this is just a little plastic toy that I don't know if you've seen these in Singapore, but it's something that kids would scroll on, and it's magnetic. So it works really, really well underwater. So we use that and have used that since the late 90s. So really non-tech tech that actually does a fabulous job. Now, I want to talk in the next part of our field survey section about some of the information that we get when we're underwater as well. So what you've got up here at the moment is two axes, and I'm going to put wavelength on the x-axis and the amount of reflectance of a certain wavelength of light on the y-axis. So this is some hyperspectral data, or basically trying to get information about how different features reflect and absorb light. And so, for example, we have a brown coral, and so you can see that over the different wavelengths of light, it reflects in certain regions more than others. And one of the features that allow us to identify different types of coral in the environment based on light reflection and absorption is the shape of this curve. So it's got these little 1, 2, 3 little bumps. Now they're really, really small, but anytime that we see that in remote sensing data, that lets us know that we have some live coral there. We can do the same, we'll get the same sorts of measurements for sediment or sand. So you can see how the shape of these two lines is different. And we can do that for all different types of features as well. So looking at how coral is different to algae, to sediment, and to rocks or turf algae there as well. And so I want to talk a little bit about the instruments that we use to get this type of information and how they've changed over 20 years. So in the late 90s, this is me standing here with one of the little instruments in my hand. And my supervisor has in this tub a piece of equipment that cost about $180,000 at the time. I'm not sure how we ever convinced him to tow it on the reef. So it is actually floating in the water. That's incredibly flat that day. So you can see it's up to nearly my knee height. And so it's in this tub with a computer. And then I've got a little cable and I'm pointing it at the coral to get this information on the reflected and absorbed light. And yeah, it is a really, really, it's a beautiful microatoll, if you like, or a coral bommy. So this is a Parietes species of coral. So you can see the stuff that we've got in that tub and a huge amount of money that is just not waterproof and really inappropriate to be in a saltwater environment, but that's what we were doing at the time. And in another study, here's another group of my colleagues, and you can see the computer equipment that they've got attached to their bodies, the laptops and the harnesses and all that sort of thing. Again, in a reef environment is a little crazy. And even to get a little bit higher up over the different reef features, these really long poles to try and get that same sort of view looking down over larger areas. And yeah, it is an Etch-a-Sketch or a Magnadoodle actually is the name of the little child's toy that I was showing before. Thanks, Sarah. So now what do I do instead? quite simply I use drones. So you can see, actually I've got, that's the same instrument pretty much that I showed you in the tub on the water surface, just tucked in under this drone here. This is now about the size of a matchbox. It's tiny and can fly on just a commercial off-the-shelf drone. Sensor itself only costs now about $5,000. The drone maybe about $1,000 to $2,000. So the price has come down considerably. The flexibility is incredible, and the amount of information that we get is better than it was back in the day. Now, here's an example of using that same type of equipment, but underwater, because we've done stuff above water and underwater as well, because we need to measure the difference and the effect that the water column has. So you can see me diving here and taking these measurements of this particular coral. And one of the biggest things that was an issue for us back then was you can actually see this cable that's coming from the sensor. It's a 10-meter long fiber optic cable, and it was attached to the boat. And again, that computer set up inside the boat. And so any wave or anything like that is pulling on this cable that was an incredibly expensive and quite fragile cable as well, that should never ever be bent as a fiber optic cable, and totally inappropriate to be using underwater, even though it was an underwater cable as well. But really difficult, because we also needed to wear a mask to communicate with the person on board, so they knew when they were taking a reading. And these masks would never ever fit my face, because they're designed for men's faces, which are much larger. And so it would never ever work for me anyway. So now the systems that we've helped to design are more contained. So you can see this is one of my colleagues here, and he's got the same system, but it's all housed inside this little underwater housing here. Incidentally, they've still made them inappropriate for women's hands. I can't hold it and dive at the same time. It's just not, my hands are not big enough to press any of the buttons. So definitely something that we need to work on more. But it now means that you're freer as a diver to go around and take these measurements without being tethered to a boat. Part of the work that we do is to also measure the incoming light. So similar sorts of instruments being used here. You can see it's measuring a white panel. So that's looking at the amount of incoming light versus the different features that we would measure. So changing that up from being off the side of a little rubber boat to something around the wrist, you can see there's that same fiber optic cable here. So this is back in 2004. And then moving on to smaller and smaller systems, and much more portable systems. And here we go, that same one again. You can see that panel completely autonomous, I guess, if you like, and not being attached to the boat to be able to capture these readings. And finally, doing the exact same sort of measurements, but this time using our drone. You can really see how small that is when it's in my colleague Steph's hand here. So really, really small instruments are now being able to capture that same sort of information. And so this has really largely changed, I would say, in the past 5 years in terms of coming towards the drone activity. But as a timeline, we are heading back, so the late 90s, early 2000s, and into sort of 2010-ish. So again, using one of those, the idea of a large white panel to measure incoming light, and doing this over a large scale. Drones are just far more efficient there. So other ways that we look at doing field work, I particularly like this little clip that I'll play for you, and hopefully it works. So this is one of my colleagues. I'm flying the drone over the top here to show what he's doing, but he has a long bar, and on that bar, through the high tech, he has 3 GoPro cameras, and each camera is capturing a photo every second. And then what he does is he brings that all back together in the lab and stitches these photos together. But one of the things that I want you to experience as you're looking at this particular footage here is how small he is. And when you think about it's now coming back, and it's going to bring into, I'm not a particularly good videographer, by the way, it's going to bring into view Heron Reef, or Heron Island, as we come up the back there. So this really helps you realize why field survey is never enough, right? You see how tiny he is and how long it would take to even field survey just Heron Reef, let alone 3,000 reefs in the Great Barrier Reef, let alone all the reefs globally as well. So this is some of the output of doing a transect like you just saw Javier swimming there. So he's bringing all those photos together and comes back with these really, really highly detailed digital elevation models, I guess, if you like, of the surface or of the surface of the substrate. So looking at the structures of the corals, the algae, and all those sorts of things. And this helps us look at different habitats and the complexity for different animals that live on the reef as well. All right, so moving out of the field survey realm and how that's changed, I want to talk a little bit about satellites, because there's been quite a big change in satellites over the past 20 years that have made a huge difference to my discipline as well. So I want to start out with Landsat, who is a series of 7 satellites that have been capturing data since the 1970s. And this is an example of the same reef using Landsat data. Landsat data has a pixel size of 30 meters. So when you zoom into all these little blocks here, they represent 30 meters on the surface, I guess. Now, one of the biggest changes I think that really came into coral reef remote sensing was increasing the spatial detail or the spatial resolution that was available from satellite data. So in 1999, we had Iconos launch, and that came down to a 4-meter pixel size. And so you can really start to see a lot more detail being available within the reef itself, and even on the island as well. So all of a sudden, we're starting to be able to get more information about what's going on the reef and the different types of habitats that are there. Still definitely not to the live coral aspect though. So we've continued to see those commercial satellites really evolve over the past 20 years. So we're coming down, further down and down in terms of the pixel size, or increasing the amount of detail that we're able to see. And over those years, that also allows us to create global coverage of reefs, but then also look at time series analysis. So having that archive of data that allows us to really draw upon and try to understand what's happening at different reefs around the world and what's happening over time as well. And while we think about that, so those data sets are ones that many of you may be used to looking at in Google Earth, for example. So I just actually want to touch on Google Earth because it is one of the things that has made it a lot easier for me to communicate my science, because most people understand Google Earth. So I can say, oh, I use satellites like what you might see on Google Earth. And this is what we see on Google Earth today. But if we want to flick back to 2005, which doesn't necessarily seem that long ago, this is what Google Earth used to look like. So you see, we didn't even have international coverage. Certainly there was no Australia in there when Google Earth and Google Maps first came out. So it's really cool to see how that has evolved over time as well, and the role that remote sensing in particular has played in developing that too. And I mentioned Landsat as being one of those satellites that we used a lot, and of course it's been available since the 1970s. But probably the biggest thing to remote sensing in general, not just reef science, is when the United States government actually opened the archives in 2008. And what used to be quite an expensive tool for me to use as an undergraduate student, I was able to buy 1/4 of a Landsat scene with my student budget to do my honours project. But now, of course, we can use as much Landsat data all around the world as we want. And so this is actually a table that you see out of a publication that I wrote many years ago that looks at the costs and benefits of different types of data that we might use for reef science. And you can see how much it used to cost and the resolution and detail that we would be able to get out of the different data sets. And so probably one of the biggest things was really making that Landsat archive open, and that's really caused an explosion of the different types of applications that we have in reef science, but more generally in environmental science as well. So moving to positional accuracy. So this has also changed a lot over the course of my career. So what does that actually mean? So the biggest thing that changed 20 years ago now, is selective availability. So if you have used a GPS device, or even just in your mobile device, at any time over the past 20 years, you'd probably be pretty happy with the location that it gives you. However, prior to May in 2000, the US government used to have I guess a bit of a mash on the detail that we got from GPS. So what you see on the left-hand side would be an estimate of the latitude and longitude of a device that was logging where it was. And so the device didn't move, but the data that it received made it look like it was moving location. So you can see it's quite a big cloud, and that's the level of uncertainty. So we're at around about plus or minus 30 meters that GPS information would give us in terms of where we were in location on the surface of the Earth. In May 2000, the US government decided to turn selective availability off, and has said that it's going to remain off permanently. Of course, they always have that option to re-scramble these messages, but at the moment what that meant was that it now pulls it in, so you have around about plus or minus 5 meters accuracy when you're trying to figure out where you are on the surface of the Earth. And this actually makes a really big difference when we're considering the spatial heterogeneity of coral reefs. So if you're looking at where you might be if you're doing any ground validation or in water validation, if you're 2 meters away or if you're 30 meters away, it makes a big difference as to how accurate our maps are going to be. And so by having that selective availability turned off, and then even by having access to RTK GPS, or the really, really highly accurate and precise GPS instruments that are now portable as well, has made a big difference in how we assess the accuracy of the maps that we're making. So you can see we use these really high-tech, not really, devices when we're looking at ground control. This is a hat, so a fluorescent hat that we put underwater with a couple of star pickets on top of that, and then we record its location, and then we'll measure that back in any imagery that we get. Javier, you can see here, he's about to swim over this target, and he's recording that target in drone imagery as well, and he's doing the exact same thing on land. And so you can actually really define where we are in space, in time. And that's largely enabled by removing that selective availability in 2000. Now, I also mentioned that when we're doing underwater work, we tow a GPS. And so basically the GPS doesn't work under the water. And so enabling a really low cost GPS to be able to know where we are as we're mapping underwater is really important. So are we on coral? Is it live or is it dead? And so we need that GPS to give us that information. And that's largely enabled by the accuracy and the small size of GPS devices that are now around. So this is actually an RTK GPS that's designed for using with drones. So basically it's just got a solar panel there, I switch it on, and I place these targets out around an area when I do a drone survey, and they're constantly logging where they are, and they'll use that to correct the information that I see. And we also now see drones that have high accuracy and high precision GPS sensors on board as well. So they're really giving us that sub-centimetre accuracy and precision in their positioning as well. So that's certainly changed a lot in 20 years. My next category is about data storage and processing. So in the background, you see a Landsat tape. So this is rather old. This is from the 70s. This image is not from the 70s. This is from outside the computer lab when I was a postgraduate student at the University of Queensland. So our good old floppy disks, which I was super stoked that a friend of mine took this photo and kept it. So one was a 1.44 meg on a floppy disk. Can you imagine actually dealing with something that small these days? So no, of course, the vending machines don't look like that anymore. And here's what we see instead. We've got our hard drives and it's nothing to ask for a terabyte, right? They're pretty cheap. And it's probably cheaper to buy like a 16 gig hard drive than it is to buy, I think it's $1.50 for this floppy drive there as well. But it's not just, we're not just limited to getting data storage in a vending machine. So I took this this photo at an airport in the US 2 years ago, and we've even got a drone in their vending machine. So, you know, why not, right? So when we think about data storage, I'm not sure how many of you used to get software packages delivered on floppy disks, and this one's Envy, so it's an image processing package that I've been using for many years now. And so you can see those, each floppy disk there that you would have to individually insert. We've got 11 disks there you need to go through. And then of course we went to the CDs and the DVDs, and now, can you imagine with the number of updates and patches that they're constantly doing, if they had to hard copy out this type of stuff nowadays, it just wouldn't work. So everything is just downloading off the cloud and getting patches constantly through and keeping things up to date. But then thinking also about digitally enabling our science is not just having data storage and software being available on the cloud, but it's being able to process those data as well. And so this is an example from one of my grad students who's processing drone data over Heron Reef and doing it on Google Earth Engine. And so really some of the power that I see moving forward into the future, that I'll talk a little bit about more in a bit as well, is looking at how we have these distributed data processing centers as well, and whether it be processing your own data or processing data through, say, Landsat, Sentinel, or other archives as well, and not having to download it onto your own machine, but getting everything stored, archived, and processed in the cloud as well. And as long as you can code, then all's good. And I find that the coding side of things I find is really, really interesting, because I do get a lot of people saying, oh, but you know, everything's with a GUI now, you don't need to code. But actually, if you really want to get the power through a lot of these data processing tools with big data, and particularly big geodata, it's really, really important to have those coding skills behind you as well. All right, so I did want to spend a moment or two looking specifically at drones, because they have been one of the biggest changes in my career. So I'm going to take you to this part of Heron Reef. And I did mention that I'm mostly interested in finding live coral. So let's have a look. The highest level of detail for any commercially available satellite sensor, this is what it looks like. So I want you to tell me in the chat, can you see the live coral? Just with a Y or an N. No, me neither. That's pretty tough, right? And so really this is the reason that I work with drones. So drone image 1, and a zoom in of the drone image. Tell me, can you see the live coral? Yeah. So all the brown stuff around the edges, and just because the other stuff in the middle, so what we'd often call rock, dead coral, turf algae, just because there's dead parts, it doesn't mean to say that the reef is dead, right? So this is just part of the reef life cycle, and as it reaches the sea level, parts will die and it continues to grow out. And I mean, underwater it looks like this, but I've shown you the example of what it's like underwater, how small you are and how much of an area you would need to cover if you were to do everything underwater. So underwater doesn't work for everything. Drones fit in the middle. So we do underwater, we do stuff on the boat, we do deploy sensors, we use drones, and we use satellites. So everything has a trade-off in the area in which we work. So do we want detail or do we need coverage? And how do we link them all together? And that's really where drones have filled a really nice niche, from that underwater stuff to the satellite stuff. But let's have a look at how things have changed. So in my right hand, on the left-hand side of the screen there, you see one of these tools that measures light reflection and absorption. And this is something I spent quite a bit of time with out on the reef in the late 90s. It's heavy, it's bulky, it's got dials on the top. It measured in 4 wavelengths of light, and it would give an answer on this little dial just here, and you had to manually write down what that answer was and then go back and make a graph in Excel afterwards, right? I have no idea how much this cost, but I know that we were very scared when we were out on the reef and were told that we were not allowed to drop it. And so basically that a far more sophisticated sensor is just sitting just underneath my drone here, and I've shown you some of the information from that now. So that photo encapsulates the equipment difference in 20 years from something that's used as a handheld device in the field to something that I don't know if it's remote sensing or if it's field equipment anymore, because it really bridges the gap between the two and does a lovely job of that. And so here's how we use drones when we're in the field. We fly backwards and forwards along predefined flight paths enabled by GPS. We take photos as we go. The drone comes back to home. And then once we bring it all back together in the lab, all these individual photos, we stitch together into three-dimensional maps. And this is something, just that level of autonomy, I guess, or even democratizing the way we capture data has just really changed science over the past couple of years. When we stitch things together, we get these beautiful three-dimensional models, and we can do that in a reef environment as well, not just on land. And so some of the work that I'm really interested in looking at is how water pools in these areas, and do we get areas that get warmer and how that affects coral bleaching, etc. But we also see a bunch of other things in our drone imagery as well. So not just limited to the live coral that I'm looking for, I always pull the imagery back and I see other things. So I do see sharks, I do see turtles, and I see rays as well. And even when we zoom into the corals, we can start to see different types of coral morphologies. And we can count sea cucumbers. So the sea cucumbers here, which are a valuable fisheries trade as well. And no one really knows how many that we have on the reef. We can fly drones at night, which is really important if we're interested in thermal imaging, which I am, because thermal imaging is important for understanding the effects of coral bleaching. So tell me in the chat, in this image here, can you see the temperature of the reef? Yeah, good, I hope not. It's a GoPro photo, so I'd actually be a little bit worried if you thought you could. But what I can do is put a thermal camera on my drone, right? And so with this type of camera, I actually can see the temperature. And you should be able to see there's a really bright feature just here, and you can see that in both images as well, right? So that we've got a buoy out there with a thermometer sitting underneath. So if I was to have thermometers all over the reef, there would just be way too many of them to be able to deploy. Or an equivalent satellite has a pixel size or a footprint of about 1 kilometer. Whereas I can really get the inter-reef variability with drone thermal data here, and look at the tide even coming in this particular image. So it's a really cool way to start looking at thermodynamics on the reef. I can put multispectral cameras on my drones, and something that I had wanted to do 20 years ago when I first started was thinking about how near infrared light effects can be seen on the reef. And so you can see these red colors, the satellite image in the background, but the drone imagery, making sure that we can capture it when the tide is right, which the satellites are limited to the time in which they overpass. The drone, I can decide, I can capture 5 times a day if I want. I can really pick the right time where the low tide is at the right time of day, when the wind conditions are right. We have that flexibility that satellite remote sensing doesn't allow us. So really cool when we want to start to map and monitor live coral. We can run drones over, like I've shown, that really small matchbox sensor to start giving us this information and working out just how much live coral we have. So just on that one point there, I would never be able to see how much live coral there is, but hey, I can recognize these 3 little bumps, the chlorophyll absorption that tells me I've got live coral at that location. I can do the same thing over different water depths, and you can see how these graphs have different shapes, and use that to be able to estimate the water depth across the reef. And here's some of the work from some of my students as well to be able to do exactly that. So not using expensive LiDAR sensors to extract water depth, but understanding the ways in which light is reflected and absorbed at different depths of water to extract estimates of water depth there as well. I mentioned the sea cucumbers. I know nothing, or I knew nothing about sea cucumbers. I just happened to see this in one of the images that I took when I first started drone remote sensing on reef. And I put it up on Twitter and I said, hey, does anyone work with sea cucumbers? And I had a couple of people get back to me, and that has resulted in a 4-year collaboration with sea cucumber people and the drone data that I collect. So now we've had students count sea cucumbers and look at the variation. We have data from 2016, 2017, and 2019 looking at their spatial distribution and patterns. And then we've also scaled up our counts of sea cucumber poo measured from a sea cucumber in a cage, I guess, if you like, to counting them with drones, to measuring that on satellites, to realize that we estimate that sea cucumbers turn over sediments or poo at about the amount of equivalent to 5 Eiffel Towers worth over the course of a year, which is a huge amount of bioturbation or sediment regeneration over the reef over the course of a year. We've moved from getting students to manually count our sea cucumbers, and I now have another master's student who's working on that with artificial intelligence, which is, again, just a leap forward in the way we're working with data that just wasn't possible many years ago as well. So out of all the things that I've shown that have changed, there are things that haven't changed, and I think it's really important that I address those things that haven't changed and where things need to change as well. So the first thing, 2002, this is from a workshop. You can see all about toys. This is on Heron Reef. You might also be able to see how diversity deficient the group of people are. But you think, oh, that's fine. That was 20 years ago, right? Well, things haven't really changed that much, unfortunately. And this is what a similar workshop looks like for me today. And even going to a major drone conference, this one in particular was attending a drone conference in 2018 in the United States, where there were more Johns, Michaels, and Davids than there were women who presented at that conference. And it's actually not good enough. So things haven't changed, but they can change. And they do change if we make an effort to change. So this particular workshop is one that I helped organize. And we were very specific about making sure that we had 50-50 gender representation at this workshop in Hawaii in 2018. And hey, what do you know? There's a lot more color there, and there are many women in that photo too. So it's really exciting to know that we can make a difference if we're conscious about making decisions about who attends and who's gatekeeping our science. And I work quite a lot in this area with school groups as well, in particularly working with young girls and their teachers to make sure that we know that they're coming through the ranks working with drones and geospatial science as well. And this is from one of our programs under our business that we run, She Maps. I also work to really try and drive, I guess, publication rates for women as well. And in line with GoPeaka as well, we have a new section within the Remote Sensing Journal, which is all about discovering diverse remote sensing disciplines and technologies, and thinking about the teams of people who go to create the science behind which we work as well, and have run a couple of special issues both in the Remote Sensing and Drones journals there as well. And I also run an annual online drone education conference that I drive who speaks, and I always ensure that it's 50% male-female representation, and from a range of countries as well. So not just focusing in the global north. So where to next? One of the biggest questions for me is how things are changing. So how do we use drone data to look at how things change over time on the reef? We've got a reasonable time series now that we're continuing to work through. A big issue for us is the water column. So get a slight breeze on the day, and now it's all of a sudden our beautiful drone imagery is really, really hard to tell where the coral is. So something that we're working really hard to get through. And I guess one of the biggest projects for me at the moment is thinking about how we can use the cloud to better share our data sets and enable people to come up with the best solutions possible. So we know that while we have people who capture their own data sets around the world, they tend to be siloed. and they don't get used to their full potential. And I want to make sure that we can actually create a global repository for drone data that people are able to use and analyze, because there's far more uses for everybody's drone data than what anyone who collects the data can use for themselves. So for example, if I capture an image where I'm interested in looking at live coral, but hey, there's a lot of information about sea cucumbers in it as well, why not make that available for other people who want to gain value from those data sets as well? And so if you are interested in anything from analysing drone imagery to providing drone imagery into a central repository, I encourage you to have a look at our latest project, GeoNadia, and jump online and join up. We've only just recently launched it. We have people from 39 countries involved already, and about 260 people signed in there too. So it would be wonderful to have some more people as we continue to evolve that project as well. So for me, the future is in collaboration and in open and what we like to call fair data, which is findable, accessible, interoperable, and reusable. I think it's really important that we act in that space as we come together to look at solving some of the really big environmental and societal challenges that we have in the future. And with that, I'm super happy to take any questions. Thank you so much for having me.